Okay, hello everyone. In a new video. In this one we are going to solve CRDP sample exam number 1 that consists of 4 exercises. Then let's start by exercise number 1. The title of this exercise is image given by a converging lens. The document 1, they mentioned document 1. Then now we can use it. Below represents a converging lens L, its optical axis and optical center O, the image focus F' and a luminous object AB. Number 1. Reproduce the above document, document 1 on a graph paper. Notice that here the direction of propagation of light is not indicated, but the direction of the positive x-axis is from left to right. Then we will take the direction of propagation of light from left to right. And whenever we need to redraw, we always start by drawing the optical axis having the same direction of propagation of light, which is from left to right. Then this is x prime. And this is x. Then the next step is to place the converging lens. So knowing that here the lens L is a converging lens, perpendicular to the optical axis, using the correct symbol of a converging lens. And the point of intersection between the optical axis and the lens L is given to be the optical center O. Now the image focus F' is located 1, 2 on the optical axis, 2 divisions in front of the lens, so this is F'. Now the object focus here is not given, and the point A is located on the optical axis in front of the lens by 1, 2, 3, 4, 5, 6 divisions. Then 1, 2, 3, 4, 5, 6. This is the point A. And the point B is located 1 division above A. A hat is found on B. And this is the object AB. And we don't forget the scale. The scale along the x-axis is given by 5 centimeters. And along the y-axis is given to be 2 centimeters. Then this is it for part 1. Now in number 2, or part 2, indicate the position of the object focus F of L and justify, and here indicate means that we need to state with the justification. So we need to locate the object focus F, knowing that we know the position of the image focus. Because F and F' are symmetric with respect to O, so this is the justification. What does this mean? Whenever we know the position of the image focus or the object focus, we can determine the position of the other. So here, because F' is located 1, 2 divisions behind the lens, then the object focus F will be located 2 divisions in front of the lens. So this is in front, and this is behind. And now in number 3, find the focal length F of L. So whenever we need to determine or calculate the focal length, we always start by writing the definition, which is given by the focal length is the distance from the optical center to the image focus. Now we are ready to calculate the focal length, which is denoted by small f. So it's the distance from the optical center, which is the point O, to the image focus. Here the image focus is denoted by F'. And we don't forget the bar because this distance may be positive or negative. Now F is equal to O F' bar, which is the distance from the optical center to the image focus. Notice that this distance is in the same direction of the positive x-axis, so it's positive. And now we count the number of divisions between O and F'. We have 1, 2. And we multiply by the scale along which you have counted the number of divisions, which is scale along the x-axis. Now then the focal length is given by tan. Since the scale is expressed in centimeters, then the focal length f will be expressed in centimeters. Then the focal length is equal to 10 centimeters. Notice that in this case the focal length is positive, which verifies or confirms that the used lens is a converging lens, because we know that for a converging lens the focal length is always positive. Now in number 4, let A prime B prime be the image of AB given by L. So we are in part 4.1. Let me make some space here. We are in part 4, or number 4, part 4.1. Construct A prime B prime and provide the necessary explanations. However, by itself the word construct means we need to trace and justify. Notice that till this moment we didn't trace any ray issued from B. Then in order to construct, trace and justify the image A prime B prime, we need to consider at least 2 incident rays issued from B. Then the first incident ray that we will consider is issued from B and parallel to the optical axis. We know that this ray will emerge passing through the image focus like this. And we don't forget the arrows on light rays that indicate the direction of propagation of light, which is given by, in this case, from left to right. Now this is the tracing of the first ray. Now let's justify it. Then an incident ray notice that this incident ray is issued from the point B. Issued from B. And it's parallel to the optical axis. It emerges passing through the image focus. And now let's consider another incident ray issued from B. We have two choices. Either we consider one issued from B and passing through the optical center, or issued from B and or passing through the object focus. So let's consider the easier, which is passing through the optical center, because it will emerge without deviation. And we don't forget the arrows on light rays that indicate the direction of propagation of light, incident ray as well as emergent ray. And now let's say an incident ray issued from B passing through the optical center. In this case, the emergent ray emerges without deviation. Emerges. Recall that we are tracing and justifying, because here construct means that we need to trace and justify. Moreover, yet we didn't answer the question, because the question is to construct the image A prime B prime. And here the image A prime B prime consists of 2 points, B prime and A prime. So we need to trace and justify B prime as well as A prime. So notice that here, because B represents the intersection of the incident rays, then this point, which is the intersection of the emergent rays, will correspond to the image B prime of B. So this is B prime. Moreover, a hat is found on B directed away from the optical axis. Then a hat will be found on B prime directed away from the optical axis like this. So we don't forget the hat, which is B prime. Now this is the tracing of B prime. Now let's justify it. Then the image B prime of B is the intersection of the emergent rays. Yet it's left to construct A prime, which means that we need to trace and justify A prime. So here, because A represents the foot perpendicular of B on the optical axis, then A prime will represent the foot perpendicular of B prime on the optical axis. This is A prime. And now let's trace the image A prime B prime. And A prime is the foot perpendicular of B prime on the optical axis. Then this is it for part 4.1. Now in 4.2, specify the nature of A prime B prime. Let me make some space. Now we are in part 4.2. Now specify, it means that we need to state with the justification the nature of A prime B prime. So we need to say what does A prime B prime represent? It's the image of AB given by L. So we need to say whether A prime B prime is real or virtual. So notice that here, because AB is located in front of the lens and the image A prime B prime is located behind the lens, then the image A prime B prime is real, because whenever the object and the image are on opposite sides, then the image is said to be real. Then let's say, since the object AB and the image A prime B prime are on opposite sides, then the image A prime B prime is real. Or one could give another justification why the image A prime B prime is real. So notice that the object AB is pointing upward and the image A prime B prime is pointing downward, which means that the image and the object are in opposite directions. Whenever the object and the image are in opposite direction, this means that the image is real. So let's say, since it is inverted, with respect to the object AB, then the image A prime B prime is real. No need to write both justifications, either of these are accepted. Now in 4.3, find the distance D between L and AB. So let's write distance between L and A prime B prime. And this distance is denoted by D. For sure, we need to find this distance graphically. So it's the distance between the lens and the image A prime B prime, which consists of 3 divisions. And we multiply by the scale along which we have counted the number of divisions, which is scale along the x-axis. Now plugging this on the calculator, then the distance D is given by 15. Since the scale is expressed in centimeters, then the value of D will be in centimeters. So the distance D between the lens and the image A prime B prime is given by 15 centimeters. Then this is it for exercise number 1. Now in exercise number 2, the title of this exercise is Laws of Voltages and Laws of Currents. The circuit shown in the document 2 below consists of, then they mention this document, now we can use it, consists of a battery supplying across its terminals a constant voltage UPN is equal to 20 volts. Then the trick in solving such type of exercises is to write and label the applied voltage and the traverse current across the electric circuit itself. Then the voltage of this dry cell or the battery is given by 20 volts. 3 electric components D1, D2, D3. They didn't mention the nature of these electric components. Then we cannot apply any specific law, for example Ohm's law, across these components. But for sure we can always apply the law of addition of the laws of voltages and laws of currents, because they are independent of the nature of the electric component itself. Then number 1, calculation of voltages. Part 1.1. Show that UAC is equal to 20 volts. So we need to prove that the voltage between the points A and C is given by 20 volts, knowing that PA and CN are connecting wires, so the voltage is given by 0, and this can be shown or proved using the law of addition of voltages. So always whenever we need to apply a law in physics, we need to mention the law that we are using. So let's say as a title, apply the law of addition of voltages. Apply law of addition of voltages. Then how do we apply this law? Always on the left we write the voltage of the battery, which is given by UPN. So always from positive to negative. And on the right hand side of this equation we write the different voltages across electric components, starting from P and ending with N, making sure that UAC will appear in this equation. Then from P going to the point A. Now from A we can go directly to C or across the point B, since we require that UAC to appear in the equation. So we'll go directly to the point C, and from C back to N, knowing that we are interested in determining UAC. Now the voltage UPN is given by 20. Now UPA is equal to 0, and the reason is given by that UPA is equal to 0 connecting wire. Now we keep UAC as a variable because we are interested in determining UAC, plus UCN. Across C and N we have a connecting wire, so UCN is equal to 0, and the reason is also given by connecting wire. So this justification here is important, and they usually give it half a mark since we didn't justify this previously. Now what's the type of this equation? It's a linear equation and one unknown. The unknown is given by UAC. Then the value of UAC is given by 20. Since UPN or 20 is expressed in volts, so the voltage UAC will be 20 volts. Now this is not the only way to prove that UAC is equal to 20 volts. We can say that the terminals of A and C are parallel to the terminals of the battery, so according to the law of uniqueness of voltages, they have the same voltage. Now in 1.2, indicating the law used, calculate the voltage UAB, knowing that UBC is equal to 12 volts. So now we know that the voltage UBC is given by 12 volts. We are asked to find the voltage UAB, and this can be also done using the law of addition of voltages. So let's write as a title, apply law of addition of voltages. Then how do you apply this law? Always on the left we write the voltage of the battery, which is given by UPN. And on the right hand side of this equation we write the voltages across different electric components, starting from P and ending with N, making sure that the required voltage, which is UAB, must appear in the equation. So let's go from point P to the point A, and from A to B, since we require that UAB must appear in the equation, plus UAB. And now from B to the point C, and from C back to N, knowing that we are interested in determining UAB. Now the value of UPN is given by 20, given. UPA is equal to 0, already justified. And we keep UAB as a variable because we are interested in determining UAB. Plus UBC, which is equal to 12 because it's given. Here no need to justify that UBC is equal to 12 because it's given. Plus UCN is equal to 0, already justified. Now, what's the type of this equation? This is a linear equation and one unknown. The unknown is UAB. So how do you solve this equation? We put UAB on one side and all the other numbers on the other side. Then 20 is equal to UAB plus 12. Then the value of UAB is given by 20 minus 12, which is equal to 8. Since both 20 and 12 are expressed in the SI, which is volts, then the value of UAB is given by 8 volts. Now this is it for part 1, which is the calculation of voltages. Now number 2, calculation of currents. Given I1 is the electric current carried by the electric component D1. So the electric current traversing D1 is denoted by I1 across the two terminals of D1. I3 is the electric current carried by the component D3. Then across the terminals of D3, we have a traverse current given by I3. The electric current carried by the batteries I is equal to 10 milliamps. Knowing that milliamps is not the SI unit of current, in order to convert from milliamps to amps, we simply divide by 1000. Then 10 divided by 1000. Then the electric current is given by the main electric current is given by 0.01 amperes. The electric current carried by the electric component D2 is I2 is equal to 3 milliamps. So this is I2. So here let me say that I is equal to 0.01 amperes. And I2, let me make some space here. The value of I2 is given by 3 milliamps. Knowing that also milliamps is not a SI unit of current, in order to convert from milliamps to amps, we simply divide by 1000. Then 3 divided by 1000. Then the value of the electric current I2 traversing the electric component D2 is given by 0.003 amperes. So here the value of I2 is given by 0.003 amperes. Now, okay, indicating the laws used, calculate I1 then I3. So this is important. We need to calculate I1 then I3. So notice the order. First we need to determine the value of I1, then we will determine the value of I3. Then we are in number 2 of this exercise. So let's first, as they mentioned, they said to calculate the value of I1 first. So notice that because D1 and D2 are in series, and we know that whenever two electric components are in series, according to law of uniqueness of currents, they have the same current. Then I1 is equal to I2 is equal to 0.03 amperes. So it's always important in physics to mention the law that we are using. So they will give you half a mark for this. Let me write it. According to law of uniqueness of currents, they have the same current. Which means that the value of I1 is equal to the value of I2 is equal to 0.03 amperes. Sorry, 0.003 amperes. And the trick in solving such type of exercises is to write the value of the traverse current on the electric circuit itself. So the value of I1 is given by 0.003 amperes. Now it's left to determine the value of I3. So notice that here the main current, which is given by A, it splits at the point A into two currents given by I1 and I3. So knowing the value of I and knowing the value of I1, using the law of addition of currents, we can determine the value of I3. Then let's say apply law of addition of currents. As a title. So they usually give half a mark for this. Now, how do you apply this law? Always on the left we write the main current in the circuit, which is given by I, delivered by the battery. And on the right hand side of this equation, we write the sum of different electric currents traversing different branches, and they are given by I1 and I3. Knowing that we are interested in determining I3. Now the value of I is given by 0.01 amperes, and the value of I1 is given by 0.003 plus the value of I3. So we keep I3 as a variable because we are interested in determining the value of I3. What's the type of this equation? This is a linear equation and one unknown. The unknown is I3. How do we solve this equation? We put I3 on one side and all the other numbers on the other side. Then the value of I3 is given by 0.01 minus 0.003. Plugging this on the calculator, then the value of I3 is given by 0.007. Since both this and this are expressed in the SI, which is amperes, then the value of I will be expressed in the SI, which is amperes. Then the value of I3 is equal to 0.007 amperes. And by this we have finished solving this exercise. Let's move to the next one, which is exercise number 3, equilibrium of a solid body. S is a solid body of mass m is equal to 300 grams. Knowing that the grams is not the SI unit of mass, in order to convert from grams to kilograms, we simply divide by 1000. Then 300 divided by 1000. Then the value of the mass in the SI is given by 0.3 kilograms. Given the gravitational acceleration is equal to 10 newtons per kilograms, which means that we are performing this experiment on the surface of Earth. Moreover, the stiffness constant of the springs given by K is equal to 2 newtons per centimeter. Knowing that the Newton per centimeter is not the SI unit of the stiffness, in order to convert from Newton per centimeter to Newton per meter, we simply multiply by 100. Then the stiffness of the spring is given by 200 newtons per meter. Now G is equal to 10 newton per kilogram. It means that for each kilogram it's being acted by 10 newtons according to the gravitational field strength, whereas 200 newtons per meter means that in order to elongate or compress the spring by 1 meter, we need to exert a force worth of 200 newtons. Now the solid S is suspended from the free end of the spring balance as shown in the adjacent document, document 3. They mentioned document 3, then now we can use it. The solid S is in equilibrium. This is important. So at any moment in this exercise, we can use the condition of equilibrium under the action of its weight W and of magnitude W and another force. So this is the value W, or the magnitude W of the weight vector W. Number 1, give the name of the other force exerted on S. So knowing that it's under the action of two forces, one of them is the weight, which acts on the center of gravity vertically downward. And here, because we have a spring, then the solid S will be directly subjected to the tension T along the string upward. So the name of the other force is given by the tension T. Now number 2, specify the vector relation between the two forces exerted on S, knowing that the solid S is in equilibrium. Then as a title we will write at equilibrium. How do you apply this condition? Always on the left we write the sum of forces acting on the solid S, and they are given by the weight plus the tension. And on the right hand side of this equation we write the zero vector corresponding for the condition of equilibrium. We don't forget vectors on these three quantities, especially the zero, because this is a vector relation as they mentioned. Now moving T to the right hand side, so W vector is equal to minus T vector. What does the first equation tells us? That the effect of both forces acting on the solid S cancel each other to give us the zero vector, which is the equilibrium. Whereas the second equation tells us that both forces have the same line of action, opposite direction, and same magnitude. Here, no need to write that in magnitude W is equal to T, because they are simply asking me about the vector relation. Now in number 3, calculate the value of each of these two forces, and the value here means the magnitude. Knowing that we have the value of m and the value of g, then the magnitude of w vector, which is denoted by w, can be calculated using m multiplied by g. No need to construct the triangle of this formula because this is the quantity that we want to calculate. The value of m is given by 0.3 and the value of g is given by 10. Plugging this on the calculator, then the value of w is given by 3. Since both m and g are expressed in the SI, so the value of w will be in the SI, which is in newtons. Then the value of w of the first force is given by 3 newtons. Notice that they are telling me to calculate the value of each of these two forces, in which we have determined one of them. It's left to determine the other, which is the tension. For example, we can apply Hooke's law to determine the value of the tension, but in this case we don't know the elongation. However, since in part 2 we have determined the condition of equilibrium, then let's say w vector is equal to minus t vector. Since we are interested in the magnitude, so let's write down in magnitude. So here in magnitude we drop down the vectors and remove the minus sign, so w is equal to t. But knowing that the value of w is equal to 3 newtons, then t in this case is equal to 3 newtons. Then the magnitude of the weight is given by 3 newtons and the magnitude of the tension T along the spring is given by 3 newtons. Now in number 4, calculate the elongation delta L of the spring. Now we know the stiffness of the spring and we know the tension. The elongation can be always calculated using Hooke's law. Then let's say apply Hooke's law. So they usually give half a mark for this statement, and Hooke's law is given by T is equal to K multiplied by delta L, knowing that we are interested in determining by delta L. So here the elongation is denoted by delta L and not X. Now constructing the triangle of this formula, here because we have multiplied, then T will be at the top, K and delta L at the bottom, knowing that we are interested in determining delta L, which is given by T divided by K. So delta L is equal to T divided by K. The value of T is given by 3. The value of K is given by 200. Now plugging this fraction on the calculator, then the value of delta L is given by 0.015. Since both T and K are expressed in the SI, so the value of delta L will be given in the SI, which is meters, since delta L represents a length, which is the elongation. And by this we have finished solving this exercise. Let's move to the final exercise of this sample exam, which is exercise number 4. The title of this exercise is given by Archimedes upthrust. S is a solid body of weight W is equal to 3 newtons, and of volume V is equal to 100 centimeter cube. Knowing that centimeter cube is not the SI unit of volume, in order to convert from centimeter cube to meter cube, we simply multiply by 10 to the power minus 6, then 100 multiply by 10 to the power minus 6, then the volume in the SI is given by 1 times 10 to the power minus 4, as after plugging this on the calculator, expressed in meter cube. Given that G is equal to 10 newtons per kilogram, the gravitational acceleration, which means that we are performing this experiment on the surface of Earth, density of water is given by rho is equal to 1000 kilogram per meter cube expressed in the SI. This is the density of water. Now they are telling us the solid S is completely immersed in water. This is important. So whenever the solid is completely immersed in water, this means that the volume of the immersed part of the solid S is equal to the volume V. Now here let me do a small sketch. Okay, so this is the container containing the liquid, which is given by water. And the solid S here, they didn't specify the shape of the solid, but in order to simplify, let's consider that the shape of the solid is given by a cube. Now S is being completely immersed in water. Now part 1, calculate the magnitude F of the Archimedes upthrust exerted by the water on S. And here, before I start, let me clarify the following. So what does this weight represent? It's important that in this case we distinguish between the real weight and the apparent weight, but simply because they didn't mention anything about the apparent weight, so we'll take this weight as a default to be the real weight. So this is the magnitude of the real weight. Let me write here that this is the real weight. Now let's get back to number 1. They are asking me to calculate the magnitude of F, in which F represents the magnitude or the value of the Archimedes upthrust exerted by water on S. So let's discuss the different methods that allows us to calculate the magnitude of F. So the first one, which is given by real weight minus the apparent weight, we know the value of the apparent weight. However, we don't know the value of the apparent weight, so this method here doesn't hold. Now another method is given by the condition of equilibrium. We can say that at equilibrium as a title, and we write that W vector plus F vector is equal to 0 vector. Knowing the magnitude of W, we can determine the magnitude of F, because W is equal to minus F factor, and in magnitude W is equal to F. Knowing that W is equal to 3 newtons, but this method here doesn't hold at all, since we don't know if the solid is at equilibrium or no. We don't know if the solid S is floating inside the liquid or at the surface. Okay, so they didn't mention anything about the condition of equilibrium. Therefore, we are left with the following method, that the magnitude of F can be always calculated using the density of the liquid times the volume of the immersed part times G, knowing that all of these quantities are given here. So let's say that F upthrust, or which is denoted by F, okay, is equal to the density of the liquid times volume of the immersed part times G, knowing that we are interested in determining F upthrust, so no need to construct the triangle of this formula. The density of the liquid, we have it, which is 1000. We know the value of G. It's left to determine the value of VI, but here we said that because it's completely immersed in water, then VI is equal to V. Then let's justify, since S is completely immersed in the liquid. The liquid in this case is represented by water. Then VI is equal to V. Now let's rewrite the magnitude of F, replacing VI by V. The magnitude of F, which is denoted by F, is equal to the density of the liquid, which is denoted by rho, multiplied by V, multiplied by G. The value of rho is given by 1000. The value of V is given by 1 times 10 to the power minus 4, and the value of G is given by 10. Plugging this on the calculator, then the value of F is given by 1. Since all of these quantities are expressed in the SI, so the value of F will be expressed in the SI, which is in newtons. Then the value or the magnitude of the force exerted by water on S, which is the Archimedes upthrust, is given by 1 in newtons. And now in number 2, the solid S is left to itself, which verifies that the solid S initially is not at equilibrium. 2.1, compare W to F. So let's do the comparison between W and F. The value of W is given by 3 newtons, and the value of F is given by 1 newtons. And by compare, it means we need to state whether W is greater, less, or equal to F. So in this case, because both of them have the same unit, and 3 is greater than 1, so it's obvious that W is greater than F. So this is the comparison. And they are telling us deduce if F sinks or floats at the surface of water, and by deduce it means that we need to use the previous part. In the previous part we have determined the comparison between the magnitudes of W and F. So knowing that, let me here sketch the vector W, and this is F. So notice that all of this sketch is not as a part of the answer. Now the magnitude of W is given by 3 newtons, which is greater than the magnitude of F, which is given by 1 newton. Recall that we are interested in determining whether S sinks or floats. So the action of W is vertically downward, and the action of F is vertically downward. And this equation tells us that the action of W is greater than the action of F. For this reason, the solid S will sink. Now let's say since the magnitude of W is greater than that of F, so in this case S sinks to the bottom of the container. Now in 2.2, calculate in this case the magnitude W apparent of the apparent weight of S. We know that the magnitude of F and the real weight and the apparent weight are related via the following formula, that F upthrust is equal to the real weight, which is denoted by W, minus the apparent weight, knowing that we are interested in determining the value of the apparent weight. The value of F is given by 1, the value of W is given by 3. We keep W apparent as a variable. So what's the type of this equation? This is a linear equation on one unknown. The unknown is W apparent. So how do we solve this equation? We put the unknown on one side and all the other numbers on the other side. Then dragging W apparent to the left hand side, it will gain another minus sign, so minus with minus it will become plus. Then W apparent is equal to 3, keeping 3 in its place, dragging 1 to the right hand side, so 1 will become minus 1. Then 3 minus 1 is given by 2. Since both of these numbers are expressed in the SI, which is in newtons, then the value of W apparent will be expressed in newtons. Then the apparent weight of this solid S when immersed in this liquid is given by 2 newtons. And by this we have finished solving this exercise. So that's it for me in this video, guys. I hope it was beneficial for you out there watching it, and see you soon in another one.